Do you know this gentleman? He is a Russian who appears on a stamp, and he does that because he is very famous. Okay, I'm not going to give you any proofs today, but I thought you might be interested in knowing how the proofs come about. And the proofs come about thanks to this gentleman, who seems to have lived for a very long time, but that's not true. He was born in 1821, and the stamp was produced in 1946. But his name is Chebyshev. And he had a wonderful inequality. And everybody should know it, so go home and tell your mother. So let's have a random variable, x. And x will have a mean value, an expectation, let's call it mu, and it's going to have a variance, so we'll take x, subtract off mu, square it, and look at the expected value of that, and that's called sigma squared. And what Chebyshev did was to prove this wonderful inequality. So let's see what it says. It says, what's the probability that x is a long way away from its mean mu? What's the probability that the absolute difference is bigger than some constant a? He showed, and you can show, because it's quite an easy thing to do, that this is less than or equal to sigma squared, the variance, divided by a squared. And this is a wonderful inequality. It works for any distribution whatsoever as long as sigma squared is finite. That's all the theory I'm going to tell you. But this is well worth knowing. So now we can use this to get some free lunch results. If the forgetting in an artificial neural network is by synaptic drift and some conditions, n1 plus n2, so it's the number of things I've learnt in the first set of associations, a1, n2, the number I've learnt in a2, should be less than or equal to n, the dimension of the weight vector. And then I need some slightly technical things. The rows of x1 are independent, and d1, the desired outputs, that is isotropic. Then these various nice results happen. The median is positive, so the value of delta that you have probability a half of being bigger than that is positive. So you're quite likely to get something positive. The expected value of delta we can work out exactly. It's given by the numbers here, n, and certain expectations. And what's the probability that delta is positive? It tends to 1 as n tends to infinity, if certain conditions are true. So the meaning of this mathematical result is that under drift, for forgetting, a free lunch is very probable. If n is big, so if you're looking at a brain with n is 10 to the 11, you're quite likely to see it. So here's a slightly more careful version. Under drift, with v being isotropic, then under these conditions, this. Right. So what I showed you just now has been theorems, but many people would say theorems don't prove anything. They tell you only about artificial neural networks, and the results were for big N. So my colleague Jim Stone did some simulations, and let's start off in an easy case, the one for which I showed you pictures, where the weight space is 2, and in each association you learn one thing. I learned one number and I learned one animal. Right, so Across the way we have delta. We have delta divided by n1. And in this histogram we see the frequencies, and we know from theory that the expected value of delta over n1 should be a half there. Okay, we get some values less than a half, some values bigger than a half. We also know that the halfway value should be positive somewhere, and we know that the probability that delta is positive should be fairly high. Well, it's nowhere near 1, because there's quite a lot of negative delta, but most of the values of delta are positive. That's, for a small example, a very small brane with n is 2. Now let's go bigger and take n to be 100 and n1 and n2 to be 50. Again, across the way, we're looking at delta over n1. The mean is a half. Yes, it is. This is a much more tightly packed distribution. The variance is much smaller. Every value we saw was positive. So there's definitely a lot of free lunch learning when n is 100. And if n was 10 to the 11, then I guess you'd have a very tall spike there. Now let's look at this picture, and across the way, across the bottom here, we have n. And we're taking n1 and n2 to be half of n. And up the way, we've got the probability that delta is positive. This dashed line is what the theorem says. The theorem says for any n, the probability of delta being positive, of free lunch learning, is greater than or equal to what we see on the dashed line. And here we can see that what is observed in the solid line, and that came from simulation, is definitely much higher than the bound given by the theorem. So in practice, free lunch learning is very likely. Right, at this stage, we had worked together entirely by email. We had not met. And then, one summer, Jim Stone came to Edinburgh, and I went and I met him, and I discovered what he looks like, which was very nice. And he's a very nice man. He took me out to lunch. It was a free lunch. It was wonderful. And the reason he came to Edinburgh was to talk at a workshop. And during the talk, somebody asked a question. And it was a very good question. The question was, what happens if forgetting happens in a different way? What happens if there is synaptic fading? So fading is when the signal gets weaker. And now, what we had said, so in drift, we had forgetting was W1 is W0 plus V. Now, W1 is W0, well, it's R times W0. So, if R is small, we're just making the signal much weaker. Let's see what happens this time.